Hi friends, today I am going to discuss about method development by HPLC. So first, to develop a method, selection of pH is the very most important parameter in method development. So if we select pH of the mobile phase correctly, then we will get sharp peaks and symmetric peaks. Then the detection will be easy, and low detection values and low LOQ values we will get. So for this, first we want to know about selection of pH. So before going to this, just remember 2 points. One is, for acidic molecules use acidic mobile phase, and for basic molecules use basic mobile phase. Why? Because acidic molecules will not dissociate in acidic environment, and the basic molecules will not dissociate in basic environment. If any acidic molecule is there, then that molecule will not dissociate in acidic environment. So it is in the unionized form. Not dissociate means it is in unionized form, means non-polar in nature or hydrophobic in nature. So by this non-polar nature, the compound retentivity will increase. So based on the retention, the separation of the impurity will takes place, and we will get the resolution between the impurities. So these 2 points you remember. First is, for acidic molecules use acidic mobile phase, and for basic molecules use basic mobile phase. After this, so how to know whether the molecule is acidic or basic? How to know? All our API drug substances are salts of weak acids or bases. Salts of weak acids or weak bases. So for all these, how to know whether the molecule is a salt of weak acid or salt of weak base? So whether the molecule is acidic in nature or basic in nature. So we will know based on pK of the molecule. We will know whether the molecule is acidic or basic by pKa of molecule. How we will know the pKa value? If it is a already literature is there, means we will search and we will know the pKa of the molecule. If it is a new molecule, then we will determine pKa by potentiometric technique or by HPLC, means we will inject the molecule sample in different pH mobile phases, and we will run chronogram. A sudden change in retention time and response will occur with sudden change in pH. So that will give you the pKa of that molecules. There is a formula for pKa. pKa is equal dRT by dpH, means this pKa determination by HPLC. So there is a sudden change in retention time with change in pH of the buffer. So change in retention time to the change in pH will give you the pKa of value for the molecule. So by this way, now we know the pKa of the molecule. Suppose, so how to select based on pKa of the molecules? Suppose if pKa of a molecule, acidic molecule, let us say all molecules having around 3 to 4, for acidic molecules pKa is 3 to 4, and for basic molecules it is around 7.5 to 9.4 around. Okay, so for example, take any acidic molecule, the pKa is 4. There is a one rule. the pH of the mobile phase should be 2 units away from the pK of the molecule. Again I will repeat, pH of the mobile phase should be 2 units away from the pK of the molecule. Okay. For example, acidic molecule pK is 4, and for this, if you want to develop a method, the mobile phase pH should be 2 units away from this. So pH is equal to pKa plus or minus 2. And I will explain here 2 points. For acidic molecules, pH should be two units below the pK of the molecule. pH of the molecule should be 2 units below the pK of the molecules. If pK is 4, the pH should be, according to this, the pH should be 2. Okay. For basic molecules, pH should be 2 units above the pK of the molecule. For basic molecules, pH of the mobile phase should be 2 units above the pK of the molecules. If basic molecule is their example, pK is, let us say, pK suppose it is 7.5. So the pH should be for this 2 units above the pK molecule, 9.5. So here, just listen carefully. Acidic molecule pK is 4. For this, the mobile phase pH should be 2 units less than the pK of the molecule. So pH should be 2. Okay. For basic molecules, the pH should be 2 units above the pK of the molecules. Here basic molecule pK is 7.5 and 2 units above this. So pH should be 9.5. Why this? Because it is according to Henderson-Hasselbalch equation. This is pH is equal to pKa plus log conjugate base by acid, weak acid. So pH is equal to pKa plus log salt by log conjugate base by weak acid. So here according to this, let us just 2 terms I will here. pH is equal to pKa plus, if for weak acid, if it is this is 100%, means it is not dissociated. Not dissociated means it is as is acid molecule. So means this is log 1 by 100. Let us assume it has log 1 by 100. Log 1 by 100 means the acid molecule not dissociated and it is in the 100% form and 100% unionized form. Means, so it is a completely non-polar nature. The log 1 by 100 value is nothing but minus 2. So here from pH is equal to pKa, this log 1 by 100 is minus 2. So from this formula we got here, for acidic molecules, the pH of the mobile phase should be 2 units less from pK of the molecules. pH is equal to pKa minus 2. For basic molecules, same. pH is equal to pKa plus log salt conjugate base by weak acid. This should be 100%. Means pH is equal to pKa plus log 100. Log 100 is equal to means pH is equal to pKa plus 2. So according to this, for basic molecules, the pH basic molecule pKa is 7.5 and plus 2. So pH should be 9.5. Here pKa for acidic molecules pKa is 4 and pH should be 2 units below, means minus 2. pKa 4 minus 2, pH is equal to 2. Here 2. Okay. By this way, for acidic molecules, if pH is 2, the weak acidic molecules in the single state unionized or non-polar nature. So single peak means 100% is in a single form. Single state means unionized form. If it is a single state, it will elute at a time and peak shape will be very sharp and very symmetric. If it is not in a single state, means some of the molecules in ionized state and some of the molecules are in unionized state, the peak will elute as a broad peak, means all the molecules will not at a time. So there will be some tailing, some problems will be there. So to get sharp peak and a symmetric peak, so we have to select the pH correctly. So based on this Henderson-Hasselbalch equation, we have to select the pH of the mobile phase for method development by HPLC. Okay. Now we selected the pH for the mobile phase. Selected the pH. Which pH we have to use? Now we selected. Suppose for acidic molecules, so pKa is 4. So based on that, we selected the pH of the mobile phase should be 2 and we selected pH as 2. Okay. pH is equal to for mobile phase. So based on the pH, we have to select the buffer. Which buffer suits for our pH, our selected pH? Based on pK of the molecules, we selected pH of the mobile phase. Based on the selected pH, we select the buffer. Which buffer suits for our selected pH? So this is how. Let us take one example. Potassium phosphate buffers. Potassium phosphate KH2PO4, K2HPO4, K3PO4. This is monobasic potassium phosphate. This is dibasic potassium phosphate. This is tribasic potassium phosphate. So our mobile phase pH is 2. Now which buffer we have to select from this? So simple. This will give pH around pK of the buffer. pK of buffer. This is 2.1, 7.2, 12. These are the pKa values of the respective buffers. So monobasic potassium phosphate having pKa value 2.1, dibasic having 7.2 and tribasic having 12.1. So just think. Here you remember 2 points. I will tell only 2 points. pKa of, don't confuse, pKa of molecule, pKa of buffer. initially we selected pH based on pK of the molecules. How? If pK for acidic molecules, the pH of the mobile phase should be 2 units below the pK of the molecule, and for basic molecules, pH of the mobile phase should be 2 units above the pK of the molecules. So based on pK of the molecule, we selected pH 2. So here one more term is there, pK of the buffer. Here pH of mobile phase. It is 2 units away. So from the pH of the mobile phase, from the pK of the molecule, the pH of the mobile phase should be 2 units away, and from the pH of the mobile phase, the pK should be near. Means at the pH value near to pK value, the buffer will work correctly. Means the buffer capacity will be more when the pK of the buffer will be near to the pH of the mobile phase. The capacity of the buffer will be more when the pK of the buffer will be near to the pH of the mobile phase. Don't confuse between these two. Here pK of the molecule should from pK of the molecule, the pH of the mobile phase should be 2 units away, and for better buffer capacities, the pK value of the buffer should be near to the pH of the mobile phase. So initially we selected, for one example we taken pK acidic molecule, pK is 4, based on that we selected pH as 2. So this selected pH 2. For this pH, which pK of the buffer is near to this pH 2? So this is near to this 2.1. Means pK of the buffer, this monobasic potassium phosphate buffer pK is 2.1. So this buffer will work, this capacity of this buffer will be more at pH 2. So we have to select this buffer for this pH. If our selected pH is around 7, then we have to select dibasic potassium phosphate. If our selected pH is around about 10, means 11 to 13, then we have to select tribasic potassium phosphate. So based on the pH of the selected pH of the mobile phase, then we have to select the buffer. So here different buffers are available in our lab. So how to select monobasic, dibasic, tribasic? By this way, based on pH value we have to select at what pH which buffer will work better. So based on that we will select. Means the pK value of the buffer should be near to the pH of the mobile phase. So the pH 2, for pH 2 mobile phase we have to select the pK having buffer having pK value 2.1, so near to 2. So we selected this one. So after this, so many buffers are available in our lab. We may confuse sometimes. Apart from this selection, sodium phosphate is there. So compare it to sodium phosphate and potassium phosphate. This potassium phosphate is somewhat better because that electrons from the nucleus in potassium phosphate away from the nucleus. Means how it is, this is nucleus and this is electrons in potassium. This sodium somewhat near. So this electrons will be easily removed, it may soluble easily. The buffer will be soluble in the aqueous medium easily. So precipitation chances for potassium buffers are very less compared to sodium phosphate buffers. So precipitation chances for potassium buffers are very less compared to sodium buffers. Sometimes we may prefer only sodium buffers instead of solubility because it may suit some selectivity. So and some other buffers also there. Borate for a neutral buffer, for neutral pH we have to use we will use borate buffer. Acetic acid is there, formic acid is there for acidic pH, and we may use triethylamine and ammonia. Okay, based on required pH we will use which suits for that molecule. For simply to develop a mobile phase, simply add for acidic molecules. For preparation of mobile phase, add acetic acid or orthophosphoric acid. Initially what we told, a single point: for acidic molecules use acidic mobile phase, and for basic molecules use basic mobile phase. So for acidic molecules, if pK value is less, then they are acidic molecules. If pK value is more, then they are basic molecules. So for acidic molecules, just add acetic acid or orthophosphoric acid for better peak shapes. And for basic molecules, just add triethylamine for better peak shapes. This simple concept. Okay. If for whatever buffers or whatever pH adjustments, if we are not getting peak shapes, means how we will get peak shapes, good peak shapes? If the molecule in the single state, means it is in the complete ionized or complete unionized in a single state, means 100% will be in one state, then we will get a single peak, sharp peak. If it is not in a single state, means it will be in a equilibrium state, ionized and unionized. So some molecules are in ionized state, some are unionized state. So the peak will not elute at a single as a sharp peak. So for some of the molecules we tried, so peak shapes are not getting improving. So then at the time we will use ion pairs. When we will use ion pairs, if for any pH at very low pH or high pH, if we are not getting improving the peak shapes, and so then we will go for ion pairs. What are these ion pairs? Why we will use ion pairs? Why peak shapes are not getting, means they are means not in a single state, ionized. They may be elute very early. If not ionized, they may elute very late and broad. So to reduce these problems for some rare molecules, we will use ion pairs. Ion pairs we will use sometimes for non-responsive chromophores also. Okay, ion pairs. What are these ion pairs? Alkyl sulfonates, means hexane, sodium salt of hexane sulfonic acid, sodium salt of heptane sulfonic acid, those are alkyl sulfonates. Okay, those alkyl sulfonates, they are acidic in nature. Alkyl sulfonates. Alkyl sulfonates used as a ion pair for basic molecules at low pH. Here, just understand, alkyl sulfonates and alkyl sulfonic acids, these are acids. So ion pair means what? It should be opposite charge. This alkyl sulfonic acid will combine with base, so it will form a molecule and it will increase the hydrophobicity, non-polarity, like that. So why I mentioned that at low pH, this basic molecules will ionize at low pH. Basic molecules will ionize at low pH. So this will ionize and combine with alkyl sulfonates. So form a new molecule, means this alkyl sulfonates will attach to our drug substance and form some bulky group, and will it impart some non-polarity to the molecule, and in a single unionized state it will be there. So then it will increase the retention and separation will be there. For acidic molecules, at high pH, because at high pH acidic molecules will ionize and combine with, here ion pair is quaternary salts, ammonium salt. So quaternary ammonium salts are basic in nature. These will combine with acidic molecules and form a complex. So at high pH means at high pH this acidic molecules ionize and combine with this quaternary ammonium salts and form a bulky group and complex. Okay. So this is about the ion pairs. Now the most important parameter pH we selected. Now selection of column. How to select while developing a method by HPLC. Simple, basic. The polarity of the stationary phase should be similar to that of polarity of the molecule. Understood what I said? Polarity of the stationary phase of the column should be similar to that of the polarity of the molecules. If molecule is non-polar in nature, the stationary phase polarity should be non-polar in nature. Simple basic concept. Because non-polar affinity will be more and it will retain for long. Retention will be more and separation will be there. If you use opposite polarity, then there will be no affinity and it will elute very early. All impurities and main peak will elute at a time and there will be no resolution. Polarity order of columns. So this is the polarity order for stationary phase of the columns. This is more non-polar and this is more polar. So C18, C8, C6, C4, these are carbon chains. Phenyl, amino, cyano, silica. Okay. Remember shortcut. These are carbon chain lengths from increasing order of increasing. If more carbon load is there, then it is a more non-polar. And here PACS, PACS, phenyl amino cyano silica. Remember that word, shortcut word. Okay. And types of columns. Types of columns. Type A. General classification is there. Type A or first generation. Type A columns are first generation columns. These are synthesized from inorganic salts. So these are synthesized from inorganic salts, though these are having so many metal impurities. Okay. Type B, not type B, second generation. Second generation columns are the columns. These will get by treatment of type A columns, chemical treatment of type A columns to remove metal impurities. So second generation columns are the columns. These will get by treatment of type A columns with chemicals to remove surface metal impurities. Okay. And type B. Third generation. Type B columns are third generation. These are synthesized from organic salts. This classification is only based on stationary phase only. Okay. Type B, third generation, organic salts. Stationary phase means support. Okay, here this is based on only siliceous support. Okay, this type B, third generation, synthesized from organic salts. Means these are very these are not having surface metal impurities. Means no need to treat these type B columns to remove metal impurities. Without chemical treatment not required for this type B generation. They are very pure in nature compared to type A or first generation columns. So type C. These type C columns contain SiH, silicon hydride groups instead of SiOH, silanol groups. Type C columns are very hybrid columns and these contain silicon hydride groups instead of silanol groups. Based on this silicon hydride groups, these are very rugged and will work at very low pH and high pH also. Okay, so silicon hydride are very stable stationary phases. Apart from that, aqua columns will be there. Aqua columns means YMC, ODS, aqueous, Frantosil aqueous, Jorbax, SB aqueous, so these type of columns will work with 100% aqueous mobile phase also. The only special use of these columns is they will work with 100% aqueous mobile phase. So aqua columns. Hybrid columns will be there. Already I explained in type C. So Xterra, Xbridge. So they will work at any wide range of pH. They are more stable and they will work at wide range of pH. Xterra especially very good for high basic analytes. One more term in columns, intercapping. What is intercapping? That in a solid support silica, the free silanol groups are there, SiOH. These will give problem while eluting a molecules. Means this may interact with the molecules and cause for the peak tailing. So the masking of these free selenal groups is called end capping. The masking of these or shielding or masking of these free selenal OH groups is called end capping. So end capping will reduce the peak tailing of the peaks. Some other terms I will explain. ODS, octadecylsilane. Means octa 8 decyl 10 silane, C18. Okay. Next, BDS. In columns they will mention like this nomenclature. BDS, base deactivated. Base deactivated silica. XDB, extra dense bonding phase. ODS, octadecylsilane. BDS, base deactivated silica. XDB, extra dense bonding phase. So means compared to normal other C18 columns, in XDB C18 the bonding phase will be more loading, more carbon loading will be there. So if you want to use highly non-polar molecule, then if our molecule is very highly non-polar, more means a very non-polarity is very more, so then we will use in that case XDB columns. Extera, these columns are very useful for basic analyte peak shape improvement. Basic analyte peak shape improvement we will use Extera columns. These will work very good for improvement of peak shape for basic analytes, remember. And SB, stable bond, we will call it as stable bond. These are especially unend capped. What is the special use of SB means? Sometimes the non-end capping. Here end capping is useful for to reduce the peak tailing we discussed. Sometimes non-end capping also will be useful for in some cases. How? That non-end capping means free selenal groups will combine with some analytes and will not combine with some analytes. So it will give you a selectivity for the analytes. So separation will be there. Some analyte will be holded by the free selenal group, some will be released. So there will be a resolution. So based on the non-end capping, there will be a specific selectivity for the analytes. So that is also sometimes useful. So we will discuss different types of columns, how to select only some of the part to select we discussed how to select the columns, but there will be a question in all of our minds that which column you have to use. So many brands, all are C18s, all are C18, all are cyano, all are every number of brands are there, 20-30 brands are there, every brand having C18 column. So what is the difference between different bands of the same carbon loading C18? So there will be a slight differences are there. So based on that the peaks will match or it may separate. First select which column will be for that molecule, C18, C8 or C4, C, cyano, phenyl or anything. Based on the polarity of the molecules, you select the polarity of the stationary phase similar to the polarity of the molecule, similar to the polarity of the stationary phase. You select first which brand, then if you selected C18, select any one C18 brand. If it is not separated, then go for another brand, because there will be slight differences from one brand of same column to different brand. What are the differences? Now I will tell. Acidity of silica. How it will influence? Already we discussed in the selection of pH. So acidity or basicity play very crucial role in the peak shape for the molecules. So selection of pH is very important, I told already. So this acidity of the silica will influence the separation. Okay. Different brands may have different slight changes in acidity, silica acidity. Next, bonding phase. Bonding phase means monomer or polymer. How the bonding phase is attached to the silica. So based on type of bonding, the brands may vary. Next, particle surface area. Particle surface area. And last final end capping. Jorbach's SB-C18, Jorbach's C18. Jorbach's C18 is end capping will be there, and SB-C18 means no end capping. So like that, small differences are there. So both are C18 only, but there will be a small slight variations in the internal arrangement. So these are the some of the differences between different bands. So based on this, the separation in one column we may achieve separation, and in another column we may not achieve. So in old column and new column also, sometimes while developing a method in old column we developed a method with old column and all impurities separated, and we procured a new column, and there will be a sudden surprise. There will be a merge in the new column. Why? Because due to this SDD some small changes, means it may be while manufacturing they may not get exactly that of old for new car. So there will be sometimes, not every time I am telling, sometimes it may happen. So this is basics of method development by HPLC per selection of pH, selection of buffer, and selection of column. If you have any doubts, please mention in the comment section. Okay. Thank you for listening. Bye.